welcome to lesson 5.2. Today we're going to look at more techniques for solving exponential equations. We're going to start with an example on something called radioactive decay. This is the process by which an element transforms into a different element. We identify something called the half-life of a radioactive substance, and that's the time required for a sample to decay to half of its initial amount. The equation for this is related to the equation for compound interest. So our initial amount is multiplied by a factor of 1/2 raised to the power of t over h, where h is the half-life and t is how long you've been observing it or how long it's been sitting there. And then a of t would be the final amount that you end up with. So we're going to be using this equation to start off by solving some problems. So in example 1, we have a radioactive substance that is decaying, and we observe that when we place a 100 milligram sample into a chamber, after 1 minute only 80 milligrams remains. So we'd like to determine the half-life, and we'll do that by using the half-life formula. We're told that the initial amount is 100. The final amount is 80. And t is 1 minute. So I can plug these things into my formula. And I want to start solving this. And the first thing I'm going to do is divide both sides by 100 to get rid of that coefficient. So I'll end up with 0.8 equals 1/2 to the power of 1 over h. And now I'll take the common logarithm of both sides. And I do this because then I can use the power law of logarithms to bring the power on the right-hand side down in front of my logarithm. I'll cross multiply and bring that factor of h up. So h times the log of 0.8 is equal to the logarithm of 1/2, or the log of 0.5. Dividing both sides by the logarithm of dividing both sides by the logarithm of 0.8, I get h equals the log of 0.5 divided by the log of 8. And this time I'm actually going to evaluate this, so I'm going to plug it into my calculator, and I get an h value, a half-life, of about 3.1 minutes. Part B asks you to graph this function. So to graph this function, we'll leave a of t unknown. We know we start with a value of 100 for our initial amount. T is our variable, and in this case our half-life is 3.1 minutes. So I could plug this into the TI-83 and graph this, and you should try that. Plug this into the TI-83. You're going to need to pick some window settings that are going to work to let you see the entire function. I would definitely practice this, because based on our practice thinking assignments, using equations and finding good window settings probably going to be something that you're going to see on this upcoming tips assignment. Okay, example 2. Now we have a question where we have powers with different bases. Yesterday, we spent time trying to manipulate the bases on both sides so that they were equal to each other. There's no easy way to do that with this question. But if we look at this and we look at the decay question we just did, these are very similar. The decay question had different bases on both sides. Here, with our different bases, we can start by taking the logarithm of both sides. So I'm going to have the logarithm, common logarithm, of 4 to the power of 2x minus 1, and that's going to be equal to the common logarithm of 3 to the power of x plus 2. I do this because now I can bring down my powers. And now I need to isolate the variable, and this becomes tricky because I need to first distribute on both sides. So I need to multiply this logarithm of 4 and this logarithm of 3 into both sides. This becomes easier if we can convince ourselves that the logarithm of 4 and the logarithm of 3 are just numbers. So when I distribute, I'm going to have 2x times the logarithm of 4 minus the logarithm of 4, and that's equal to x times the logarithm of 3 plus 2 times the logarithm of 3. I'm going to continue solving this by taking any term that has an x in it and bringing it to the other side of the equal sign. And I'm going to take any term that doesn't have an x in it, and I'm going to bring it to the right-hand side of the equal sign. Algebraically, I'm doing everything that you've done since grade 9. I'm changing signs as I move things to the other side of the equal sign. On the left-hand side, I can now common factor a factor of x out of both my terms. So that leaves me with 2 times the logarithm of 4 minus the logarithm of 3 is equal to 2 times log 3 plus log 4. Finally, now I have x isolated on the left-hand side, so my final step would be to divide both sides by 2 times the logarithm of 4 minus the logarithm of 3. This is my exact answer, and we prefer keeping our answers in exact form. But if the question asked me to, I could find an approximate answer, say to 2 decimal places. By plugging this into my calculator, my approximate answer would be about 2.14. One final example for this video. Here we have an equation 2 to the power of 2x plus 2 to the power of x minus 6 equals 0. This is a tricky problem because we have now 3 terms to deal with. The properties that we were looking at previous to this involved only having one term on either side of the equal sign. So something like 4 to the power of x equals 6 squared Okay, we have one term on either side of the equal sign. This is where we're able to easily take the logarithm of both sides. There is no way that I can manipulate this equation that I'm given so that I only have one term on either side of the equal sign. So I'm always going to have at least two terms on one side of the equal sign. So the strategy for this question is to write the equation in a different form. I'm going to write the equation in the form a times z squared plus b times z plus c equals 0. So I'm going to write it in quadratic form. And my substitution that I'm going to make is z equals 2 to the power of x. This first term, 2 to the power of 2x, I can consider this as 2 to the power of x squared. So I'm going to make this substitution. I have now my z squared term plus z minus 6 equals 0. So my coefficient a is 1, my coefficient b is 1, and my coefficient c is negative 6. And I identify these three coefficients because I'm going to solve this equation now using the quadratic formula, where z is going to be equal to, quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So plugging in the values that I've identified, a is 1, b is 1, and c is negative 6, I have negative 1 plus or minus the square root of 1 minus 4 times 1 times negative 6 all over 2. Okay, continuing to solve. I get negative 1 plus or minus the square root of 25 all over 2, which becomes negative 1 plus or minus 5 all over 2. So z could be equal to 2, or z could be equal to negative 3. Before we finish this question, we need to remember that we made a substitution. So z isn't equal to 2, and z isn't really equal to negative 3. We said that z is equal to 2 to the power of x. So 2 to the power of x is equal to 2, or 2 to the power of x is equal to negative 3. We still haven't solved this question. We were trying to find which value of x would make this statement true. So that's where part C comes into play. We need to identify any extraneous roots by trying to solve for x. So 2 to the power of x equals 2. This is one of those questions where I have the same base on both sides. So I can drop the bases, set the exponents equal to each other. So one of my possible solutions is x equals 1. My second possible solution, since I don't have the same base on both sides, I can take the common logarithm of both sides. And here we see that I'm finding the common logarithm of a negative number. I can't do that, which means that this is not a solution. So the only solution to this equation is x equals 1. Okay, I would definitely suggest looking over this problem again. It's a problem that often comes up on tests. I am going to go over one additional example very similar to this tomorrow at the start of class. If you have any questions about it, you should bring them at that time. Otherwise, thanks for watching.